This conference will now be recorded.
Very good evening, students. We had been discussing PYQs. So we had started with JEE Main 2020, 3rd September. This is the first session, maybe the morning session or the first shift. Questions are almost over. We have few questions to complete this first session. Then we'll discuss JEE Main paper on 3rd September for the second shift. Okay, so let us first start with the questions remaining in the first shift. So there are two parts in the JEE Main paper. Okay, so one is section 1 or part 1, part A, section A, where you will be given multiple choice type questions and all questions you have to attempt. Okay, all questions you have to attempt. So multiple choice will be there. Okay, but in the section B there will be questions, numeric questions up to some decimals. So section B will be numeric. So there actually you have to give the values. Okay, so there you have to give the values, and there will be 10 questions. Out of 10 you have to attempt 5 questions. So total 30 questions you have to attempt. Sorry, I think 25 questions. Total 25 questions you have to attempt. 20 in the first part and 5 in the second part or section B. Here there will be 10 questions and here there will be 20 questions. So out of 20 you have to attempt all 20 questions, and out of 10 questions you have to attempt 5 questions. So let us go for the section B part questions. Let us see how questions comes. See, in this question, a cricket ball of mass 0.15 kg is thrown vertically up by a bowling machine so that it rises to a maximum height of 20 meter after leaving the machine. So there are bowling machines, so which can continuously throw balls so that a batsman can practice well. Okay, practice for a long time without the help of any bowler. If the part pushing the ball applies a constant force on the ball and moves horizontally a distance of 0.2 meter while launching the ball, the value of F is dash in Newton. You have to find out what is the value of the force. See, let me make you understand the problem once again. See, there is a cricket ball, so there is a moving part. Okay, there is a cricket ball which is actually a moving part. Suppose this is a moving part. Okay, when it hits with certain force. Okay, so this moving part is actually has to move some distance. Okay, x. Okay, if the part is pushing the ball, applies a constant force on the ball and moves horizontally a distance of this, then what is the force applied on this ball such that the ball is actually going a maximum height of, so it is just going height of maximum height from the horizontal, say 20 meter after leaving the machine. All right. So what is the force here? So like you have to first recognize the problem with which concept you have to do. See, this ball is given certain force. That means it has certain initial velocity. With that, it is moving up to certain height. Okay. It is actually let me see. Yeah, this is vertically up. Okay. So you don't need to consider this. This is vertically. It is actually moving vertically. I think you can just think of the machine part like this. It is moving. Okay. So this is ball here, and this part comes and hit. Okay, suppose it was here, it comes and hit it. Okay, all right. So it applies certain force and moves horizontally while ball is actually going up like this. Okay, so this goes up to 20 meter. So it has certain initial velocity when it was pushed by the machine, part of the machine. Okay, so let us say that is v0. If that is the case, and then height is given. Okay, so we can find out what is the velocity given. Okay, so that is root 2 g into h. After getting that, see, the ball has certain mass, so there is a change in the kinetic energy. It was earlier at rest. Okay, there is a change in the kinetic energy. Okay, it was at rest, ball was at rest when it is given this much velocity. That means there is a change in the kinetic energy. And what for, like work energy theorem, right? Work energy theorem says work done is change in the kinetic energy, change in kinetic energy, right? This is work energy theorem. You might be thinking how we can use work energy theorem here. Let me tell you how. This is work energy theorem. Energy theorem. See, this part is moving up to certain distance horizontally, right? And the force is F. Let me write the work done then. F into X, right? F into X is equal to change in the kinetic energy. See, earlier velocity was 0. Now velocity is just when it is hitting, velocity is V. So I know the kinetic energy, change in the kinetic energy will be half m v naught square. Okay. So from here actually I can find out the force. Okay, so m v naught square divided by 2x. So m is 0.15 kg. V I know, v naught I know, v square I know, 2 g and h divided by 2 into 0.2 meter, right? So if I do the calculation, see how it goes, like this. Then this g is 10. Let me write it. So 1.5 into 2 into 10, it is given, and h is 20 meter, 2, and this is 0.2. I have already done some operation with that. So this becomes 15, right? This goes with this goes with 10. So you will get actually 150 Newton. Okay. So what is the force? Force is 150 Newton. Okay. So force is 150 Newton. I hope you have understood this. Let me move for the next problem. So this problem says a person of 80 kg mass is standing on a rim of circular platform of mass 2 200 kg, rotating about its axis at 5 revolutions per minute. Okay, so situation is something like this. Let me draw it a little bit bigger. Okay, so you have to consider this is circle. Okay, circular platform, kind of a disc. Okay, circular platform means kind of a disc. Okay, it is kind of a disc. That means you can just, okay, so it has a rim like this. Rim in the sense edge, just like rim of cycle. Okay, so this is axis of its rotation, which goes through its center of mass and perpendicular to its plane. Suppose it is rotating with certain omega that is given, that is 5 revolutions per second. It is given minute, 5 rpm. This is given. Now when this is 5 rpm, when the man, a person of 80 kg, is just standing over here. Okay, let me draw here. A man standing over here. Okay, a man is standing over here. Okay, just to, okay, let me give some respect to this man and draw nicely. Okay, so say this is, okay, so the man is standing here. Okay, so man is standing here at the edge, and it has mass. I'm sorry, whatever. No, I think it has gone. Let me draw it once again. Okay, so this is, okay, so representative mass I'm taking. This is the mass of 80 kg. Let me take this as small mass. Okay, smaller mass is there. Okay, and this is the circular disc. It has bigger mass, capital M. Okay, so small m is given as 80 kg, and capital M is given as 200 kg. So the question is, okay, so it is moving with this man at the rim with angular speed 5 rpm. Okay, revolutions per minute. The person now starts moving towards the center of the platform. Now this man starts moving this way towards the center. Okay, what will be the rotational speed in rpm of the platform when the person reaches to the center? When the person comes here, when person reached here, then what will be the rotational speed? So this question actually is from conservation of, so this type of problem can be solved with the concept of conservation of angular momentum. Conservation of angular momentum. Sorry, conservation of angular momentum, not energy. Okay, conservation of angular momentum says I1 I2 is equal to, sorry, I1 omega 1 is equal to I2 omega 2. So what is omega? Omega is the rotational speed and I is the moment of inertia. So initial moment of inertia, initial rotational speed, final moment of inertia, and final rotational speed. I have to find out final rotational speed. So I1 omega 1 divided by I2. But this is the problem now. How to find out I1? I1 means initial moment of inertia of the system. So initial moment of inertia of the system is the moment of inertia of the rotating this circular object, circular platform, which I have taken as disk, and the man which is sitting or standing at the rail. See, at this situation you have to actually apply parallel axis theorem to find out the total moment of inertia of this system about this axis. Okay, about the axis of the rotational axis of the disk, okay, or this circular platform. So circular platform has its own moment of inertia about its center of, like, about the axis passing through its center of mass, and which is perpendicular to its plane, is given by m r square by 2. And this mass is supposed at r distance away, so I can write the moment of inertia as m r square. This is parallel axis theorem. Okay, but how to find out I2? What is I2? So in this I can actually do a little bit of simplification here. So r square by 2 capital M into 2 into small m. This I2, what is I2? I2 is the moment of inertia when this man has actually reached to the center, and the axis of rotation is through the center of mass only. Then what will be the moment of inertia I2? I2 will be the moment of inertia of the disk or this circular platform alone. Then since, see, I know in rotational motion, it's any mass, if it is sitting on the center, like on the axis of rotation, then it doesn't rotate at all. So there is no rotational inertia associated with the mass which is sitting on the axis itself. And also we know moment of inertia is actually going to be anyway it is going to be proportional to r square, since it is sitting on the axis. So moment of inertia due to the small mass will be 0. Okay, so the moment of inertia of the whole system when the man reaches to the center will be m r square by 2 alone. Okay, all right, now things are done. I have to do the calculation part. Okay, so what is the calculation? Calculation will be very simple here. See, omega 2 I have to find out. So I1 I have found out r square by 2 capital M plus 2 into small m divided by r square by 2 capital M, right? This I can strike them out. Okay, so this I can strike out, and I can put the value of capital mass is 200, and this is 2 into 80 kg divided by, oh I see, there will be omega 1 as well here, omega 1, omega 1. So omega 1 is 5, you know that, 5 rpm. So I have to find out the omega 2 in rpm, so that's why I don't have to do anything with that omega 1. And see, this is 200, so this will be 360 divided by 200 into 5. This will come in rpm. This will be 40. This is 9. So this is 9 rpm. rpm. I hope students you are understanding this. Okay, so this first of all you need to understand that this problem could be solved from the law of conservation of angular momentum. Second thing, what are the moment of inertia? When the object was here, the moment of inertia will be found out by using parallel access theorem. When the person at the center, it is exactly at the center, then moment of inertia will be just the moment of inertia of the circular platform. But see, there could be sometime a question related to this kind of problem. See, there will be given like, see, omega 1 will be given. Okay, so it is rotating circular platform. Okay, and suppose first there was an insect or ant or something, so which is crawling down, crawling towards the center, and at certain point it is seen that the angular velocity is omega 2. Then what will be the, like, at what position the ant has come from the center? Okay, that can be another type of question. So in that case, you have to again use the parallel access theorem. So you have to use that arbitrary r. Okay, so radius obviously for this will be given, so you have to find out r prime where it has come. Okay, so here then I2, say I1 omega 1 will be I2 omega 2. So here I1 was the moment of inertia of this and parallel access theorem at this position. Okay, suppose if it is this has radius capital R and this insect has mass small m, then I1 will be again, if it is circular thick disc like thing, then mr square by 2 plus m small capital R square. Okay, now this was I1, but I2 will be mr square by 2. This is for the disk, and now it is actually m small r square, and this small r you have to find out that small r will be actually from the center. Okay, from the center, so that small r you have to find out. Okay, where the omega 2 will be given. Okay, it is not very tough to find out because omega 1, say I1 omega 1, omega 2 as well. You have to find out what is the value of I2, and from there you have to do this calculation. Okay, so that you find out smaller. All right, so this was corollary from here. And sometime there will be like there was nothing in the beginning, then there will be suppose a like a small mass of wax is sticked. Okay, just fall on this and just stick to this. Okay, then like stuck at certain distance. Okay, that distance may be given, then you have to find out what is the I2 omega 2. So this kind of question may come. Next, let us discuss the third question. A bakelite beaker. So guys, yeah, so here the answer will be 9 rpm. Okay, 9 rpm. Next problem is a bakelite beaker has volume of capacity 500 cc at 30 degree. That means at room temperature. When it is partially filled with Vm volume of mercury, it is found that the unfilled volume of the beaker remains constant as the temperature is varied. You have been given volume expansion coefficient of beaker to be 6 into 10 to the power minus 6 degree per cc. It should be cc actually. Okay, so and this for mercury, okay, per degree centigrade, anyway, per degree centigrade, and this for mercury it is 1.5 into 10 to the power minus 4 degree per degree centigrade. But gamma is the coefficient of volume expansion, and Vm in cc is close to. I'll tell you, this question is saying that suppose there was a beaker initially. Okay, initial means it has its original volume. Okay, let me just do properly. So there was a beaker. Okay. So it has original volume. This will be flat anyway. Okay. Okay. So it has volume 500 cc, which I am writing here V0 original volume 500 cc. Now it is filled with mercury, and this volume is found to be Vm. Okay, Vm. Then the rest of the portion, you look this portion, this portion, this is empty. Now at room temperature, the original volume of the beaker is 500 cc, and the mercury volume of the mercury is Vm, and rest of the volume of the beaker is empty. Now when the temperature is varied, it is seen that this volume, the empty space or empty volume, is remaining constant with temperature variation. Okay, does not change at all. Okay, so in that case, what is the volume of this mercury? That is the question. So I can say, suppose this is the volume of mercury, and this is the volume of original beaker and bakelite beaker. Okay, so the volume, see, the volume which is remaining or empty space is actually given by V minus Vm, right? Now when we increase the temperature, then this original volume of the bakelite also will change, and volume of this mercury also will change because of thermal expansion. But it is said that this volume does not, this empty space, volume of the empty space does not change, it remains the same. So see, look, this will be the equation, isn't it, where V0 is given by V0 prime is given by V0 plus V0 into gamma V0 into gamma beaker into delta T, change in the temperature. And this Vm prime, this is the change or so modified volume of the mercury after increasing temperature, and that also could be written as Vm plus Vm into gamma of mercury, okay, into delta T. Now if I put this V prime and M prime here, then I will get an equation. Let me see. So V0 minus Vm, this is on the left hand side, it is all right. So on the right hand side, see, I'll just put these values, V0 plus V0 into gamma beaker, I'm writing just B into delta T minus Vm minus of Vm into gamma mercury into delta T. So these guys, V minus Vm, I can make them separate, plus this V0 gamma B minus Vm gamma M into delta T. This is my equation now. This is Vm, V0 Vm. Look, this will actually cancel each other when I take this to this side, and then ultimately it says that V0 gamma B is equal to Vm gamma M. Okay, so from here let me see. Okay, I have space, so Vm will be written as VO gamma B divided by gamma M. Now what is VO? 500 cc. Into 10 to the power. What is gamma given? That is 6 minus 6 here divided by gamma M, that is 1.5 into 10 to the power minus 4. Okay, I hope this is all. Let me do the calculation. So if I take to this side, okay, 500, 110, I multiply here 10 to the power 4 here, 6 into 10 to the power minus 6. These two along with this will cancel this, and in the down there will be 15. So this so it gives, actually this will be in cc. Okay, cc. So this is 20 cc. So the answer for this is 20 cc. So Vm will be equal to 20 cc. All right, go to the next problem. This question says, when a long glass capillary tube of radius this much, let me write, small r is given as 0.15 centimeter. This is the radius of the capillary tube, which is dipped in a liquid. The liquid rises to a height of 15 centimeters, small h. So this is actually a problem from capillary rise. If the contact angle between the liquid and the glass is close to 0, that means theta is 0, the surface tension of the liquid in millinewton per meter is dash when closest to dash, closest integer I have to write, and this is given, rho is given and j is given. So rho is given 9 into 900 kg, 900 kg meter cube, kg per meter cube. Okay, and g anyway you can take 10 meter per second square. Okay, look here, you need to actually directly write down the formula for the capillary rise. You know that this is 2t cos of theta divided by rho r and g. So where everything is given, only you have to find out t. T is then h rho g r divided by 2 cos theta. Cos theta, here theta is 0, that means cos theta is 1. Okay, okay, so this, now if you just put the values, nothing else, you have to just put the value and do the calculation. So this is 15 centimeter 10 to the power minus 2. I'm writing in SI unit. This is 900 kg per meter cube. G is 10 and R is given as 0.015 centimeter. Okay, this actually I'll write in meter, or let me write it. See, I'll write here itself in meter. See, if it is, see, this is already 15 into 10 to the power minus 3, and I have to make it again minus 2, so it will be 10 to the power minus 5, 10 to the power minus 5. So 15 into 10 to the power minus 5. All right, so down it is g, sorry, 2. Okay, so look here, these two, this cancel this one, and there will be 110 also I can cancel. This is then 2 to 5 into 10 to the power minus 4 by 2. This I can divide with 2. So this will be 1, again 1, 2, okay, so this 4.5. Okay, so this is the thing here. So 112.5 into 10 to the power minus 4. Okay, so if we write in milli Newton, then it is actually, I don't know whether I have done some mistake in the calculation. 15 centimeter. Okay, this is fine. 900. Oh, I had left 9 actually. There will be one more 9 here. Okay, so anyway, do the calculation. So rest of the things are same. Do the calculation. I'll just give you the value here. If you do the calculation properly, you must be getting value nearly, so up to the closest decimal you will get nearly 0.1, sorry, 101 millinewton. Okay, millinewton. So this is the value, 101, nearly 101. Okay, now let us go to the next problem. I think this problem is again from SIP 2. Okay, this is from SIP 2. Let us do this question, solve this question. A block of mass, a block of mass A block of mass m attached to a massless spring is performing oscillatory motion of amplitude a on a frictionless horizontal plane. Okay, if half of the mass of the block breaks off when it is passing through its equilibrium point, the amplitude of the oscillation for the remaining system becomes f into a. The value of f is how much? Okay, that is the question. So there are options over here. So look what happens. Uh, See, with amplitude, this is a formula you can note down, that this product will be always constant. A1 omega 1 is equal to A2 omega. So here A1 is given as A, but we don't know what is omega 1 and omega 2. That we can find out actually. Okay. See, for a spring, here actually what happens, question is like this. There is a horizontal plane, there is a spring mass system, say. Okay, it is oscillating, and when it actually crossing, it is crossing its equilibrium position, then become, the earlier mass was m, now its mass has been 2. So when its mass has become m by 2, we can find out what is the omega, right? We know omega is equal to root over k by m. Omega square is equal to root over k by m, right? That means, you know, this omega is directly inversely proportional to square root of m. All right. Then I can write omega 1 by omega 2 equal to m2 by m1, right? m2 by m1. What is m1 and what is m2? m2 is m by 2 and this is m. That means you get here 1 over 2. That means 1 over root 2. This is what is omega 1 by omega 2. Now I have to find out what is the amplitude. Okay, here omega a1 is given as a, so I have to find out a2. That means a1 omega 1 divided by omega 2. I know this ratio omega 1 by omega 2 and this is a. So this is 1 by root 2, right? So 1 by root 2, a by root 2, then a by root 2. So f means what then? F means 1 by root 2. So this is the answer. Okay. Option B will be the correct answer here. So the point you need to remember is this one. Keep in mind that a1 omega 1 is equal to a2 omega 2. And also you have to know how to find out this ratio omega 1 by omega 2. This is from this formula, as you know. Okay. Now again from shift to second problem, and hopefully today we'll stop with, yeah, so this is the last problem for today's session. Let us solve it attentively. Hydrogen ion and singly ionized helium atom are accelerated from the rest through the same potential difference. The ratio of the final speed of hydrogen and helium ion is close to speed. See, you know, when you have a potential difference, a region of potential difference V, and you want to accelerate that particular ion or charged particle having some charge q, if you just leave it here at rest, it will be accelerated to this region, and then its energy will be q into v, and that q into v will actually be converted into kinetic energy of the particle. Okay, so this is the kind of potential energy, so which gets converted into v square. Okay, half mv square. This is actually equivalent to current. So this v and this v are not same. I'll write this v as capital V and this v as small v. This is the speed. So if you want to know what is the speed, then q into the potential difference is the speed. Okay, now I have to write what is v. V is 2q potential difference divided by m. Okay, this is the one, this is the actually speed. Now if I write for hydrogen ion, it has charge 1, so this potential is this, and this mh, let me write this as mh. And for helium ion, what is the charge? It is actually 2 into, okay, the potential difference with the same potential difference, so v is v, but q is different, that is actually 2 times of the charge of the hydrogen. Then I'll write here 2 divided by m helium. So m helium is actually 4 times. Okay, let me just do this ratio first. Ratio of the speed of hydrogen, then speed of hydrogen divided by speed of helium two V by mH, and here it will be mHe divided by 4V. So this V goes up. Okay. Now you have got here half into this mH is actually 4 times, right? So 4 times of the mass of hydrogen. So 4 times of mass of hydrogen, and this is mass of hydrogen is like this. So this will actually become, okay, let me check whether I have done some mistake. No, hopefully this is for 4. Okay, so let me see this 4. Okay, 4B, fine. Okay, 1 2 also was there here, so that I have not considered, I think. Oh, that has become 4 to be over there. Okay, I think I have. Okay, let me just do one thing. Let me keep this Q hydrogen, and here instead of writing the things here, Q helium, and then put it here so that we get clear idea here itself. So V anyway will be getting cancelled. So you will get, so MHE into Q, okay, MHE, and here will be into 2V QH, and down it will be 2V Q helium and mass of hydrogen. So this V goes up, this two goes up. Say MH is 4, this is 1 divided by, this is 2 times, okay, so 2 times, and this is 1. Helium singly ionized ion, I see. Okay, so I had done a little mistake. So 2He4, sorry, it is actually 2He4. This is the atom. When it is singly ionized helium ion, it has charge, single charge only. Okay, so I don't have to multiply charge 2. Okay, this charge also will be 1 only, because it is singly ionized. Okay, I have just thought this is singly ionized means it has only one charge, same charge as hydrogen. Okay, same charge as hydrogen. So QHE is actually, this is for singly ionized, this is having the charge of QH itself. Okay, so then this is 1, so you will get actually 2:1. So first option will be the correct answer for this question. Okay, so this is all for today. Thank you for your patience. Bye for today. We'll then next we'll take up the questions for the second shift of the same date, JEE 3rd September, okay, 2020. All right, so thank you for your patience. Bye for today.